Welcome to the Deep Dive. Today, we're plunging into a topic that's all about making those incredibly powerful language models we use every day work even faster.
Hmm.
Imagine chatbots that understand complex queries instantly, or, coding assistants that autocomplete whole chunks of code almost before you finish typing.
Making things feel really seamless, not clunky.
Right, that's the promise of the innovation we're diving into today.
Yeah, we're looking at some recent research from FAIR at Meta. It's titled Set Block Decoding is a Language Model Inference Accelerator.
Okay.
And our mission really is to unpack how this new approach could dramatically speed up language model generation. We're talking like 3 to 5 times faster.
3 to 5 times.
Yeah. And crucially, without any loss in performance, it tackles a really critical bottleneck, trying to make these models much more responsive, more efficient in practice.
Okay, so to really get why set block decoding, or SBD, is a big deal, we probably need to understand the problem it's solving first, right? The challenge with current models.
Definitely. So these large language models, LMs, they're built on the transformer architecture, scaled up massively, hundreds of billions of parameters sometimes.
Which gives them amazing abilities like understanding language, generating code.
All sorts of things, but actually using them in real time in applications, that's where you hit a bit of a wall.
What are the specific costs? Where's the slowdown?
Good question. The process of getting a prediction, inference, or sampling, it has 2 main stages.
Okay.
First, there's pre-filling. That's where the model processes your initial prompt, like the question you ask it. That part's usually pretty efficient, handling lots of tokens at once on the GPU.
Right, gets the context sorted quickly.
But then comes the decoding stage.
Okay.
And this is the real bottleneck. Here, the model generates the answer token by token sequentially, one after another.
Oh, okay.
And for each new token, it has to read the entire model weights and all the cache information, the key value pairs, from the GPU memory, again and again.
So it's incredibly repetitive.
Very. And that step-by-step process makes it slow. It often completely dominates the total time it takes to get an answer.
So the standard method, next token prediction, or NTP, it basically means the model thinks one word at a time. It's like trying to have a fast conversation by sending one word per text message.
That's a great analogy. It just inherently limits the speed. Each word waits for the last one.
Accumulating costs, both time and computation.
Right. And people have tried to fix this before, haven't they, with things like speculative decoding?
Yeah, that's one approach. Using a smaller, faster draft model to generate chunks quickly, then having the big model check them.
Which works, but adds complexity, right? Now you need 2 models.
Or other methods like multi-token prediction, which might add extra bits, extra heads to the model architecture to predict several tokens.
Also adding complexity or changing the core model structure.
Okay, so this is where set block decoding, SBD, comes in. The paper calls it a simple and flexible paradigm. That sounds promisingly different.
It is. The idea is to accelerate generation by smartly combining both the standard next token prediction, NTP, and something called masked token prediction, or MATP.
MATP, like filling in the blanks.
Sort of, yeah, like predicting hidden words in a sentence. And SBD does this within a single architecture. No extra models, no big structural changes.
And the key difference is?
It can sample multiple future tokens in parallel. And importantly, these tokens don't have to be consecutive, not necessarily right next to each other in the sequence. That parallel, non-consecutive prediction is quite novel.
That sounds powerful. And you mentioned practical advantages.
Big time. The research highlights several key points. No architectural changes needed. No extra training hyperparameters to tune.
Okay.
It stays compatible with standard KV caching, which is important for efficiency.
Yeah.
And you can implement it just by fine-tuning existing models.
So you take a model like Llama or Qwen.
Exactly.
Yeah.
They fine-tuned Llama 3.18b and Qwen 3.8b in the paper. You're not building from scratch, you're enhancing what's already there.
That makes it much more accessible, presumably. Less complex than juggling multiple models or adding new output layers.
That's the elegance of it. Single model simplicity, aiming for significant speedups.
Okay, so let's get into the mechanics. If NTP is one at a time and older parallel methods had issues, how does SBD pull off predicting multiple, potentially non-consecutive tokens together?
It uses a framework called SET, or mask, parallel decoding. Instead of just predicting the next token or trying to predict a whole block of future tokens independently.
Which is hard to do accurately.
Right. SBD does something more nuanced. It masks some future tokens within a block it's trying to predict. but then it lets the model see an arbitrary subset of the other future tokens in that same block.
Ah, so it gets some context from within the future block itself.
Precisely. It uses that partial future context to predict the masked tokens. And because it's designed this way, it can predict those masked tokens in parallel. This arbitrary order and parallel sampling is the key flexibility.
That's clever. Letting it peek ahead, but only at certain parts, to help fill in the blanks elsewhere in the block.
Exactly. It avoids the pitfalls of trying to predict everything independently or sequentially.
So how does it decide which tokens to mask and predict in parallel? Is there a system for that?
There is. It uses advanced sampling algorithms. The paper highlights one called the entropy-bounded sampler, or EB sampler.
Okay, entropy-bounded, what does that do?
Think of it like a smart scheduler. It looks at the masked tokens the model could predict and figures out which ones have low mutual information.
Meaning they don't depend much on each other.
Right. They're relatively independent. If two words don't strongly influence each other's probability, you can potentially predict them at the same time without much loss of accuracy.
Makes sense.
The EB sampler identifies these low-dependency tokens and allows them to be decoded in parallel. It uses just one main setting, a hyperparameter called gamma, symbolized as
Gamma, okay.
and this gamma lets you tune the trade-off. You can adjust how aggressively it predicts in parallel, balancing speed versus potentially a tiny bit of accuracy shift, though often negligible.
And the model itself is still a transformer.
Fundamentally, yes. But it's trained specifically for this hybrid approach. It uses causal attention for the past tokens, meaning it only looks backward like standard models.
Standard autoregressive behavior for the history.
Correct. But for the future block it's generating, it uses bidirectional attention. Tokens within that future block can actually see each other when being predicted.
Ah, that bidirectional view within the block is what enables the parallel prediction using that partial context we talked about.
That's the key architectural nuance. It allows that look-around capability specifically for the block being generated.
And the training itself mixes predicting the next token and these masked tokens.
Yes. The training uses a combined loss function. It includes the standard NTP loss plus a loss for the masked token prediction, MATP. This dual objective is crucial.
All right, so let's talk results. The theory sounds good, but did it actually work? What did the experiment show?
The results reported are pretty compelling. They fine-tuned those Llama and Quinn 8B models.
Using what, instruction data, reasoning data?
A mix. Around 70 billion tokens of mixed reasoning and instruction data. And they found SBD led to a 3 to 5 times reduction in the number of forward passes needed.
Fewer forward passes means faster generation, basically.
Directly correlates, yes. And importantly, they achieved this while maintaining the same performance level as the models trained normally with just NTP.
No accuracy drop.
Not according to their benchmarks. They show results in figures and tables, things like coding benchmarks like LiveCodeBench, reasoning tasks like Math 500, GSM-8K, Human Eval plus EDMS. The SBD models consistently match the performance of the baseline NTP models.
So you get the speed up 3x to 5x fewer steps without sacrificing the quality of the output. That's impressive.
It really is. That's often the trade-off you face, but they seem to have navigated it well here.
And that gamma parameter, how does that factor into the results? Could you push the speed even higher if you were willing to accept a small performance hit?
Yes, the GOM value provides that tuning knob. They found that lower values of gamma preserve the accuracy very closely while still giving those 3x to 5x speedups.
Okay.
If you increase gamma, making the entropy bound looser, you can get even more acceleration, more parallel prediction, but that might come with a slight, often small decrease in performance on some tasks.
So it gives developers flexibility. If you need absolute maximum speed for, say, a real-time system, you might tweak gamma up slightly, accepting a tiny quality dip.
Exactly. Or if accuracy is paramount, you stick with a lower gamma and still get a very substantial speed boost. It offers that fine-grained control.
Now, digging a bit deeper, the research also looked into why it works, didn't it? Through ablation studies, what did they find was essential?
Yeah, those studies were insightful. A really key finding was about the training loss. Remember, we said it combines NTP and MAPP loss.
Right, the next token prediction and the mask token prediction.
Well, they tried removing the standard NTP loss during training, just relying on the masked prediction objective.
What happened?
The model's performance dropped significantly. It failed to maintain the core autoregressive capabilities, the ability to generate coherent sequences properly.
Ah, so you really need both. You need to keep training it to predict the very next token like normal, alongside learning the mask prediction trick.
Precisely. That combination is essential for SBD to work effectively and maintain the base model's quality. Removing the NTP part broke its fundamental generative abilities.
That makes sense. And getting this SPD performance up to par with the standard models, did that require a lot of extra training time or steps?
It required a comparable amount of fine-tuning. During the supervised fine-tuning SFT phase, the SBD models needed about the same number of training steps as the standard NTP models to reach performance parity.
So around 34,000 iterations in their experiments, I think.
Something like that, yeah. It shows it's not really a training shortcut, but an inference enhancement that needs proper fine-tuning to integrate well. You have to bake the SBD capability in during SFT.
Got it. And they also did some theoretical analysis, a roofline model.
Yes, to bridge the gap between fewer forward passes and actual wall clock speedup, because sometimes theoretical step reductions don't translate perfectly due to hardware bottlenecks.
Right, overheads and memory bandwidth can get in the way.
Exactly. So they did this roofline analysis for an 8B model on an H100 GPU. They looked at computation versus memory bandwidth limits.
And the conclusion.
The conclusion was strong. The 3x to 5x reduction in forward passes should translate almost directly into proportional wall clock speedups in practice.
Why is that?
Because the overhead of processing a slightly larger block in SBD compared to a single token in NTP was found to be minimal, maybe just a few % for a block size of 16, for instance.
So the main time cost is still the forward pass itself, and since SBD drastically reduces the number of those passes,
the overall time taken drops significantly. It provides good evidence that the speedups aren't just theoretical, but should be realized in actual usage.
Okay, this deep dive into set block decoding, it really paints a picture of, well, a clever and effective way to tackle that core inference speed challenge. It's about getting the model to think, or at least generate, in parallel blocks, not just one token after another, making it more efficient.
Yeah, it really does offer a compelling route to much faster language model inference, that 3x to 5x reduction, translating to real-world speedups while keeping performance and avoiding complex architectural changes. That's a strong combination.
And the fine-tuning approach makes it practical for models people are already using.
Definitely. It's a solid piece of engineering building on existing foundations.
Thinking beyond just the numbers, this kind of parallel generation could really reshape how we interact with these models in real time, couldn't it? Lower latency applications suddenly become more feasible.
Absolutely. And maybe think about the energy savings too. Fewer computational steps could mean lower power consumption for inference, which is a growing concern. What other efficiencies might emerge if this parallel approach becomes more standard?